Hello, let's take a look at the problems assigned out of section 4.4. First up, we are given a rational function here. The top is of degree 1, the bottom is of degree 2, and everything is already factored, so there are not going to be any common factors to cancel here. That's good. That means the domain is just given by setting the denominator equal to 0. It's all x except this. So it's all x except x equals 0 and x equals minus 12. Those are the only x's that will make the denominator 0. Otherwise, there's no obstruction here. To locate the intercepts, we find x-intercepts by setting y equal to 0. We find y-intercepts by setting x equal to 0. Y-intercepts are easier to find, so I'll get y is equal to 0 plus 8 over 0 times 0 plus 12. This is 0 over 0, which does not exist. It has no y-intercept. Let's take a look at the x-intercepts. I set x plus 8 over x times x plus 12 is equal to 0. Now this looks pretty difficult, but notice if I cross-multiply the denominator of the left over to the right, you get x plus 8 is equal to 0 times x plus 12, which is just 0. We kind of see a general pattern here, provided that this rational function is just one numerator over one denominator, and if I set that equal to 0, multiplying the denominator will still leave a 0 up here. In other words, the only way a rational function in its proper form of just single numerator over single denominator, the only way that will ever equal 0 is exactly if the numerator is equal to 0. And in here, that corresponds to x equals minus 8. So we do have an x-intercept, but we do not have a y-intercept. Determine vertical asymptotes. Vertical asymptotes, if the rational function is in reduced form, okay, is exactly the x's that make the denominator 0. So this is already in reduced form because there were no shared factors, which means finding the x's which make the denominator 0 has already solved this. So the vertical asymptotes are x equals 0 and x equals minus 12. We did that in the first part. Now we want to determine the behavior of the graph on either side of each of these vertical asymptotes. Okay, so I'm going to erase much of the work that we have down here so that I can draw a picture. Okay, notice we have already found the intercepts. That's the only stuff I'm erasing. Okay, I'm going to keep the information about the intercepts because we are eventually going to want to graph this function. So I'm going to copy that up at the top. X equals minus 8, and there is no y-intercept. Okay, so let me just write that up here. Intercepts, x equals minus 8, and there is no y-intercept. Okay. Now we have two vertical asymptotes, x equals 0 and x equals minus 12. Actually, let me make this one minus 12. And over here will be x equals 0. So my function is r of x is equal to x plus 8 over x times x plus 12. What I like to do to answer how does this look on opposite sides of each asymptote is play a little game. Let's suppose x is just above 0. Okay, so I'm looking what happens to the right of the vertical asymptote x equals 0. If I'm examining this vertical asymptote, but I look just to the right, I'm looking at x's just above 0. What happens to my function? Well, r of x, something slightly larger than 0 plus 8 is approximately 8. And something slightly larger than 0 plus 12 is approximately 12. But down here, I have something small and positive. So my numerator just looks like 8, but if I have something very small times 12, that's going to be pretty small. But it's still positive. I have a positive number times 12. And 8 divided by something very small will be very big. But 8 divided by a positive number is positive. So overall, when x is just a little bit bigger than 0, r of x is big and positive. So it goes up to the right of this vertical asymptote. Okay, let's see how that changes if I plug in something just below 0. Okay, so I'm going to erase much of this work. So what changes is the following. If I plug in something just below 0, now I've put in something small and negative here, but nothing else has changed. Okay? Being very close to 0, whether you're larger or smaller, 0.01 versus negative 0.01, x plus 8 is still very close to 8, and x plus 12 is still very close to 12. The only thing that's really changing significantly is the number x. It's still small, but what's changed is it's no longer small and positive, it's now small and negative. And a small negative number times 12 is small and negative. 8 divided by a small number is still big, but 8 divided by a negative number is negative, which means for values of x just to the left of 0, we get big negative numbers, so the vertical asymptote must go down as I approach that from the left. Okay, so I'm going to erase all of this, and we're going to do similar arguments for what happens when x is near negative 12. So, first, if I plug in something just a little bit bigger than negative 12, so just above negative 12, well then, negative 12 plus 8, that's going to be very close to negative 4. X is very close to negative 12. But what about negative 12 plus x? Okay, x is just above negative 12. So if I add 12 to that, okay, I'm looking at this term right here, x plus 12. X is slightly larger than negative 12. So the negative 12s cancel out, but I was actually slightly larger, which means what remains is something positive and small. If I was slightly bigger than minus 12, then when I add 12, I'm slightly bigger than 0. I am small and positive. A small positive number times negative 12 will be small and negative. And now I have negative 4 over a small number, that's going to be big, but negative 4 over a negative number, that's going to be positive. So this is going to be a big positive number. If x is just above minus 12, the result is a large positive number, so it goes up. I didn't draw that very well. It goes up as you approach this vertical asymptote from the right. What about from the left? Well, if I plug in x just below negative 12, in other words, negative 12.001, just slightly to the left. Well, when I add 8, I'm still very close to negative 4. X is still very close to negative 12, but now when I add 12, since I started out slightly smaller than negative 12, when I add 12, I am very small, but I'm going to be negative. Now my denominator is negative 12 times a small negative number. That's still small, but it's now positive. And negative 4 over a small positive number is going to be big, but it's going to be negative. So, as x is close to negative 12, but to the left, I'm getting out big negative numbers. The asymptote must go down here. Okay. This sort of argument will get much faster as you practice it more. Okay, determine the horizontal asymptotes. Well, looking back up at our original r of x, the top is of degree 1. The denominator is of degree 2. Since the denominator has larger degree, the horizontal asymptote is automatically given by y equals 0. And now we are asked to graph it. So we happen to know there's a y-intercept at x equals minus 8. So if I go ahead and throw down that horizontal asymptote of y equals 0, at x equals minus 8, I know I get out y equals 0. Okay, so the graph has to come down and go to this point. There is no other point where I have y equals 0. This was the only x-intercept. So I can't do something like come down and come back up. I can't do something like go up and come back down later. Either of those pictures would produce a second y-intercept, and there isn't one. So the only option is for our graph to come down and then join this over here. Similarly, to the left and to the right, I can't ever cross my horizontal asymptote, because then I'd have another value of x that produced y equals 0. Since I don't have any more x-intercepts, I cannot cross my horizontal asymptote to the left, so I must approach it like this. And I cannot cross it to the right, so I must approach it like that. So there is a reasonable graph of this function. It approaches the horizontal asymptote but does not cross it on the left and right. It does cross it in the middle because there is that one y-intercept of x equals minus 8. And we knew that it crossed it from above and then below as we go from side to side. Okay, that it crosses this line of y equals 0 from above to below because we had done this work of determining the behavior to the sides of the vertical asymptote. It was up here and it was down here, so it must have crossed exactly once. So we've got a pretty similar question here. We're going to do all the same steps, but we're going to work through it a little faster because we just did one like this. I'm going to go ahead and factor a 7 out of the numerator and a 5 out of the denominator. Observe that now I have fully factored rational functions and there is no shared factor to cancel out. This means the domain and the vertical asymptotes are both solved by setting the denominator equals to 0, which is quickly seen to be equivalent to x equals minus 4. So the domain is all x except for that, and x equals negative 4 is the only vertical asymptote. Okay. Intercepts are solved, well, first of all, the y-intercept is solved by letting x equal 0. Now, if x equals 0, observe that 7x and 5x are both 0, leaving behind exactly 7 over 20. So the y-intercept is pretty quickly found to just be 7/20ths. Now, the x-intercept is solved by setting y equal to 0. But remember, a rational function is equal to 0 if it's in reduced form only when the numerator is equal to 0. And the numerator is quickly seen to be equal to 0 exactly when x is equal to minus 1. So those are our intercepts, and that's all of them. Okay. Also, our rational function is a degree 1 polynomial over a degree 1 polynomial, which means the horizontal asymptote is given by the ratio of the leading coefficients, the numbers multiplying the largest power of x in the numerator and denominator respectively. The largest power of x in the numerator is 7x, and the largest power of x in the denominator is 5x. So our horizontal asymptote is that ratio, 7 over 5. Okay. Now let's go ahead and throw down our vertical asymptote of x equals minus 4, and we're going to go ahead and see what happens to the right and to the left. So we're going to do similar reasoning that we did before. We're just going to talk through it a bit faster. Now notice, if x is very close to negative 4, my numerator is very close to 7 times negative 3, or negative 21. Okay, so if x is close to negative 4, then y is close to negative 21 over 5 times, and here's where it becomes important to keep track of what's going on, because if I add 4 to something close to minus 4, I'm close to 0. And close to 0 has two possibilities, close to 0 and positive, close to 0 and negative. Close to negative 21 is always negative, okay? But close to 0, that's where it gets tricky. So if x is slightly bigger than minus 4, that denominator will be positive. But I have negative 21 in my numerator, which means overall I will be negative. And if the denominator is small, negative 21 divided by that is very big. So if x is just a little bit bigger than negative 4, I've got negative 21 over 5 times a tiny positive number. 5 times tiny number is still tiny. 5 times positive is positive, but then negative over positive is negative. And a negative over a tiny number is very big. So if x is to the right of minus 4, I get large negative numbers. So I have to go down on the right side. On the left, however, this x plus 4 term will now be slightly to the left of 0 and slightly negative. And now I'm going to have a negative over a negative, and that's going to turn everything into a positive result. Okay, so I have to have that behavior on either side. Now I'm going to go ahead and complete the graph by putting down my axes. Here's y equals 0. Here's x equals 0. I also want to label, let's see, the horizontal asymptote, which is y equals 7/5. So I'll put that up here. I may need to move some stuff I already drew just in the interest of space. Okay, this is going off to infinity, which means it needs to be much larger. I want to keep it away from that horizontal asymptote. Let's go ahead and label our intercepts. If x is 0, y is 7/20ths. That's in between 0 and 7/5. And the only time y is 0 is when x equals minus 1. So that's the only time the graph is going to cross that axis, okay? Which we can complete by going something like this. My drawing isn't so great. This should be like a more consistent kind of curve, but you know, we're just trying to draw as best we can. So I want to approach this, go through those 2 points, and then go down to minus infinity, something like that. I'm not the best drawer, and no one should really expect you to be either, but if you go ahead and graph this, it should look more or less like that. Okay, we're going to do the same thing down here. This is already factored in the numerator as 5x. The denominator factors as x plus 5 times x minus 5. There are no shared factors, so there's nothing to be tricky about there. What's the domain? All x except for plus or minus 5, which means those are also the vertical asymptotes. Okay. The only time there isn't going to be an exact match between the domain and the vertical asymptotes is when there are shared factors to cancel, and there are not here. To find the intercepts, well, the y-intercept is solved by setting x equal to 0, and we just get 0. The x-intercept is solved by setting y equal to 0, and the only way the numerator is 0 is when x is 0. So the intercept is the same point, 0, 0. Let's go ahead and throw down our vertical asymptotes, x equals minus 5, x equals 5. So if x is very, very close to 5, one way or the other, 5x is close to 25, and x plus 5 is close to 10. The only thing that's changing is x minus 5. So I'm going to have a positive number up here, and down here I have positive times whatever happens to x minus 5. To the right, that's positive. To the left, that's negative. So overall, positive to the right, negative to the left. For x equals minus 5, some things do change, okay? The numerator is now close to negative 25, and this is close to negative 10, but this negative and that negative will cancel out. So overall, this will still result in a positive number up to determining what happens to x plus 5. Well, if x is slightly larger than negative 5, this will be positive, and if it's slightly smaller, this will be negative. So again, I end up with positive numbers overall to the right and negative numbers overall to the left. Now I'm just going to finish the graph by putting in our axes. Oh, we haven't done the horizontal asymptote, sorry. The top, the numerator is of degree 1 and the denominator is of degree 2. Since the denominator is of larger degree, the vertical asymptote is automatically y equals 0, or just that x-axis, so it's already in there. Okay. The only time I cross the x-axis is at any y-intercepts, and there's only one of them, and it's at the origin. So the only time the graph is going to cross that axis is at the origin. So I link those up like that. Now these approach the horizontal asymptote, but I already know it's not going to cross it because there are no other roots. And there's a reasonably good graph of the function. All right, now we've got a function. We have a concentration of a certain drug in a patient's bloodstream, Find the horizontal asymptote. So this is actually quite fast. So this is a degree 1 numerator and a degree 2 denominator. So the only horizontal asymptote is given by y equals 0, which means as t is increasing, c of t is approaching 0. That is what is happening to the concentration of the drug. As time goes on and on and on, the concentration is getting smaller and smaller and it's approaching 0. This is what we hope happens, that eventually it just gets passed out of your bloodstream and gets smaller and smaller with time. It would be a bad thing if the horizontal asymptote was a positive number. If the horizontal asymptote of a drug concentration was a positive number, then as time went on, you'd be approaching this fixed value, but never getting less than it. It would sort of represent you can never get rid of it. And that isn't a realistic scenario, assuming your organs are functioning properly. So a horizontal asymptote of y equals 0 simply represents the concentration of the drug getting smaller and smaller, getting closer to 0 as time goes on.